morning, everyone. We shall continue our lectures. Today, I'm going to start chapter 4, which is the chapter for mean flow equations. This is a very exciting and important chapter because in this chapter, I'm going to explore the Navier-Stokes equations, the transport equations for fluid, considering turbulence. It's unlike chapter 2, which we did not consider turbulence, but in this chapter, we do consider turbulent flow, and we would formulate and close all the equations to be able to solve them. If you remember, we talked about mean velocity field with this symbol, two angled brackets representing the statistical mean. We said velocity was a field, vector field, so this u is bold-faced u, which depends on position vector x and time. We also introduced the concept of Reynolds decomposition for you, which we said you can decompose any instantaneous velocity field into a mean velocity field plus the turbulent fluctuating part. It is very customary to use capital U for inside angle brackets for mean velocity and a small u to show fluctuating velocity. Both of these mean and fluctuating are still vector fields. So they are both vector fields. Okay? The first identity I want to explore is the requirement for continuity. So let's explore if the continuity equation applies to the mean and turbulent fluctuating fields. The continuity equation implies that all of the instantaneous, the mean, and the fluctuating fields are solenoidal, which means their divergence should be 0. And in fact, we will claim that they are. So the mean operation commutes inside the divergence. So mean of a divergence is divergence of the mean. So that's the first thing I want you to appreciate. So even for the mean velocity field, the divergence is still 0, which means the continuity equation is satisfied. Not only that, even the divergence of the turbulent fluctuating component is 0. So even the fluctuation field meets the continuity criteria. Okay, so in other words, I just said this mean operation commutes inside divergence. Okay, so that's good. Now let us develop our transport equations. I promised to you that I will explain the total or material derivative. Okay, so there's a very specific way we define material derivative. There is a difference between like derivative, normal derivative as we know it, and material derivative. So what is the difference? If you want to take derivative of some variable in physics, Well, in the most simple sense, you derivative with respect to you take the derivative with respect to one variable. Take the derivative of something with respect to time. df over dt, finished. Alternatively, you could take derivative over a space. I mean, dv over dx, finished. Material derivative somehow combines both temporal and spatial derivatives all together. And the concept is this. Most fluids move when in action. Material derivative tells you how any quantity of interest is varying in both space and time. Okay? Think about it. If I bring a sensor here and place it in airflow in this room, I take the derivative of, let's say, temperature with respect to time. D capital T over D small t. This gives me the change in velocity, change in temperature only in this location as a function of time, right? I did not move the sensor. So I just told you how temperature varied with the change in time. The sensor was here. Now imagine I move the sensor along with the flow, which means that if airflow was going in a certain way, I just followed the airflow with my sensor and not only considered the temporal derivative of, let's say, temperature, but also the spatial derivative. So now you are moving with the fluid parcel, and you take both derivatives, both in space and time. That's called the material derivative. So it's comprised of a storage term, and it's comprised of an advection term. The storage term is derivative with respect to time, and the advection term is derivative with respect to space. And you can take the material derivative of anything. It doesn't have to be a component of velocity, let's say uj. It doesn't have to be u, v, or w, or u1, u2, u3. You can take the material derivative of anything, any property, temperature, density, concentration of some chemical in fluid flow. It could be defined over anything. But here we are considering material derivative of a component of velocity, uj. This could be u, like this component of velocity, let's say in this direction. It could be the other component of velocity. Now, I'm interested to now know what's the mean of the total derivative, right? Remember, this chapter is all about mean flow equations. So I should somehow find what the mean of the total or material derivative should be. And I claim that that mean is temporal derivative of the mean variable plus a spatial derivative of the product here. And that follows from the fact that the mean operator commutes inside the derivative. Well, first of all, the mean operator is linear, so you can apply to each term separately, and then for each term, the mean commutes inside the derivative. So this requires no proof. This is just the property of statistics or math. Okay? And you will see shortly that this term is a little complicated because, well, here I had velocity, now I have the mean of velocity, so I can deal with that quite easily. But here, something came up. The mean of a product of velocity components came up, which requires more attention. And now I want to explore that for you. So what is the mean of the product of two velocity components? Well, I can simply expand each component, right? Component I, this could be U1, component J, this could be like U2, or this could be U, this could be or this could be v. I have two components of velocity. I can express each of them as the sum of the mean plus turbulent fluctuating parts. I'm using Reynolds decomposition to express each term, which was instantaneous, as a function of its mean plus the fluctuation. And remember, this product is still inside the mean operator. Now I carry the multiplication term by term, right? I have this mean multiplied by that mean, the result shows up here. I have this mean multiplied by that fluctuation, and I have this fluctuation multiplied by that mean, they show up here, and then I have the product of the fluctuations which show up. Now I can claim that these two terms are zero. In other words, well, the mean operator is a linear operator, right? So I can say that the mean of the bunch of terms is equal to the sum of each mean, right? So if you look at this mean, if you look at that mean, well, this mean can jump out of the bigger mean because it's already a constant number, right? Do you agree with me? So after you take the mean, well, this mean comes out because it was a constant. And then finally, you can see the mean of the fluctuation that remains must be zero. Therefore, each of these terms must be zero. I can also put a very short picture to it. By very definition, if you have some velocity component and you measure a turbulent field over time, it's going to fluctuate. And we talked about this many times before. It's going to fluctuate. The mean of the all the fluctuating signal would be something like u, and the deviation would be little u. Okay? By definition, the mean of the fluctuation must be zero. It must be zero by very definition. If it was not zero, it would contribute to the mean of the signal. You know what I'm saying? It must be zero. There's no way it can't be zero. The mean of the fluctuation is always zero. So then the mean of the product of the two instantaneous velocity components simplifies to the product of the means for the two components plus the mean of the product of the fluctuations. And this is a new result. So if I go back to the transport equation for the J component of velocity, so this is the equation I showed you in the last page, right? Well, I showed you this equation. Now I want to determine the fate of this last term, which was not easy to deal with, but having expressed the mean of the product of the two random fields, now I can express that nicely. You see that here. Okay, so nothing happened except for the fact that I replaced the mean of the product of the two velocity components by product of the means plus the mean of the multiplication of the fluctuations of the two components. You can take a step further and apply the partial spatial derivative into this term. Well, so you're going to need the derivative of the first term plus the derivative of the second term. Taking derivative is also a linear operator, so you can just apply it to a bunch of terms and sum them up. Note that the variable of interest here is over which I'm taking derivative is uj. So ui, the mean of ui, comes out, and whatever remains is only the spatial derivative in the I direction, this could be x, y, z, of the component I was looking at. Okay? And then likewise I apply the spatial derivative to the product. This is a new term now. If you compare this equation to chapter 2, chapter 2 we ended here. Chapter 2 we ended here. But if the flow is turbulent and you do Reynolds averaging, a new term pops up, which we have to deal with. Also note that here, index I repeats in this term, like index I, ui, and then partial xi. What should we do if index I repeats in differential equation? What was this known as? This was known as Einstein notation. So you have to repeat, apply index I over all possibilities. In other words, I repeats. Okay? We will show you examples of this repetition and how you would expand it in the following discussion. Okay, so now I know what the material derivative is. One of the things that you should realize is the second step, if you know something about the product rule in calculus, if you have derivative of a product of two functions, then the derivative is the product of the first times the second function plus the first function times the derivative of the second. So you must know this from calculus that if you want to take the derivative of two functions multiplied by one another, you might recognize this one. So you get derivative of the first times the second plus the first times the derivative of the second. This might sound familiar. This is known as the product rule. And it's the product rule that allows me to simplify this term, because I'm taking the derivative of the two products. One of them would actually end up zero. One of the terms out as a result of expanding the product rule would be zero. And that would be partial of u over partial of ui over partial of xi. This must be zero because we had the continuity equation as a requirement. Okay? Let me expand this for you. I mean, really, using the Einstein notation. So you have something like this. I mean, you open a book in differential equations or whatever, or physics. You see this. You see this term. What should you do? Well, index I repeats. You must expand this over all of the possible components. So you should do u, the first component, partial x, plus partial v, that's the second component, partial y, plus partial z, partial w, partial z. So what I did, because index I repeated, I had to expand it over all possibilities of components and then add them up. This is the very requirement for the continuity equation. So in fact, it's the continuity equation that I wrote for constant property fluids, like constant density or incompressible flow. So that's why I claim this to be zero, and it must be zero. We already said it should be zero in here. Okay? Continuity equation. In fact, this is the same thing, right? Taking the divergence of the velocity field, a component of it, is the same thing as what I wrote here. Two different mathematical notations, and you can consult the appendix to check the definitions. The next thing I want to do is to introduce the mean substantial derivative. And this is just a matter of definition. There is no proof. I just want to define this symbol. I just want to define this symbol over bar capital D, over bar dt. I just want to define it as the mean substantial derivative in a way that you take the partial derivative with respect to time of something, it could be anything, density, temperature, a component velocity, plus mean velocity vector times divergence of whatever I'm interested in. And remember, I could be doing this to any quantity of interest. I mean, in the brackets, I could put anything. I just define this new operator as the mean substantial derivative. And by this definition, I can zip the formulation for material derivative of the mean of a material derivative, because I can just say it's the material derivative of mean plus spatial derivative of the fluctuations. If you look here, all I'm doing, I'm zipping these two components into this. If you like, I could be doing this to uj. Right? I'm combining those two terms and calling them the mean substantial derivative. But the last term still remains. I still keep that at the end. So I have sort of a new notation. So let's read what each term is or labeled. The first one was the mean of the material derivative, right? So mean is the angle bracket of the material derivative. This other term is material derivative of the mean. You see what's happening? So be careful with the words. The mean of material derivative is different from material derivative of the mean. Plus, I call this Reynolds stress term, because if you remember from last time, this is a component of a Reynolds stress tensor, right? I and J and all the rest. So this was a Reynolds stress tensor. I'm taking a spatial derivative of that. So you see, I carefully label each term. In physics, if you want to learn physics well, anytime you write an equation, you should label or sort of name each term, and you should know what each term is. And throughout this course and this book, I've tried to do it as much as possible. Anytime I show you an equation, I tell you what each term is called. Okay? So Same convention here. And this equation is now interesting because this last term is problematic. I mean, nobody knows what they should do with this term. And most of the difficulty in turbulent flow analysis is dealing with that term. I mean, whether you're doing experimental work or whether you're doing modeling work, it's hard to know what that term is. It's hard to measure it and it's hard to model it. So let me emphasize, the mean of material or substantial derivative velocity field shall not be confused, nor is it equal to the mean substantial derivative. So remember that. So these two things are different things. Now that I know what material derivative is, and now what I know what it is for mean velocity components, the next step is to insert that into the momentum equation. Next step is to insert that into the momentum equation for the mean velocity. Remember, the objective of this chapter is to derive equations for mean flow. So, equation for the mean momentum. So, I had the material derivative of mean, that was the left-hand side. Then I had surface forces. We showed you this as the Laplacian of the mean velocity component. What was this symbol called? Anybody remembers? Viscosity. Which type of viscosity? Kinematic or dynamic? Kinematic. Kinematic, because I divided mu by density rho already. Remember, mu is mu over rho. Okay, so that's dynamic. Viscosity, that's kinematic. Then the Reynolds stress term shows up here. In fact, it was on the other side of the equation, right? Because it belonged to the material derivative, but I just bring it to the right-hand side and group it here with a negative sign. So what happened? It was on this side. It was on this side, on the side of the material derivative, right? But I took that term, brought it to the other side of the equation for momentum. That's why it became negative. And finally, I have normal and body forces. What was this symbol P for? What does P stand for? Pressure. How about pressure? It was pressure. Okay. The main difficulty in turbulence work is the Reynolds stress term. That's the main difficulty in this equation, and it's hard to deal with. This term, in fact, shows an instance of a closure problem. And the closure problem can be summarized as follows. In turbulent flow, equations are always lacking. In other words, in turbulent flow equations, one always encounters more unknowns than the number of equations available to close the system of equations. If you have, let's say in mathematics, you have 5 variables, unknowns, you can technically come up with 5 equations and solve for the unknowns. 5 unknowns require 5 equations. But in turbulence, this happens usually. Let's say you have 5 unknowns, but you only have 4 equations. You're always behind in the number of equations that you need to solve for all the unknowns. That always happens, when you do Reynolds stress decomposition, Reynolds decomposition of variables. So if you like, this is now a new term, right? Well, I got a component of velocity, ui, and then I have this new unknown. So I have one equation and two unknowns, so to speak. You see what's happening? So this is known as the turbulence closure problem, and it never ends. Last year, one of the students came up with this phrase: never-ending route. No matter how far you go, you never reach the end of the destination. So you always have to come up with new equations and new approximations to close this one last equation for the last unknown that popped out, so to speak. So that's the idea here. Let me now talk about tensor properties. Now we want to define the Reynolds stress more formally. We told you it's a tensor, well, obviously, because it depends on two directions or multiple directions, I and j, to be defined. And I claim this to be these terms to be a component of a second-order tensor. The second-order tensor must have 9 components. Well, because in the Cartesian space, you have 3 directions, okay? And you have the order of the tensor. So this is the number of directions. It's either x, y, or z, or 1, or 2, or 3. And then I'm telling you it's a second order. So that's the order of the tensor. Basically, I'm combining 2 of those directions, right? 3 to the power of 2 is 9, which means that the second order tensor in the 3-component Cartesian coordinate system must have 9 components. And this is not new, it's the same. I mean, you've seen this before. This tensor, there's the 9 different ways you can combine these components. On the diagonal here, you can think of it as a matrix. I mean, sort all these components in a matrix 3 by 3, where over each row, the first component is varying, like this was 1, U1, U2, U3. Over the row, the first component varies. Over the columns, the second component varies. So kind of organizing it nicely. The diagonal components of this tensor happen when the 2 components are the same. So you have U1, U1, U2, U2, U3, U3 on there. And we sort of show these as U1 squared, U2 squared, U3 squared. We know them as normal stresses, while the off-diagonal components are called shear stresses. Okay? So in other words, so for example, this is a normal stress, and this one, which is off-diagonal, is a shear stress. The normal stresses would interact with the control volume. Remember the cube? We said on each face of that cube, the control volume of the fluid, these stresses act. The normal ones would try to compress or stretch the control volume. The shear ones would want to push it sideways. That's why we call shear. But we're talking about a turbulent mechanism to apply these stresses, right? So it's a nice concept. I want to define a new variable, the turbulent kinetic energy, as half of the trace of the Reynolds stress tensor. If the Reynolds stress tensor could be thought of as a 3 by 3 matrix. The trace of a matrix is the sum of the terms on the main diagonal direction of the matrix. So in this case, the main diagonal is u1 squared plus u2 squared plus u3 squared. The trace is the sum of those. And I say put a 1/2. We call this the turbulent kinetic energy. So that's big deal. And I'll explain in a bit. But let's see the mathematical properties. See, I begin using the Einstein notation. Index I is repeating here in this notation. That means I have to sum up all the possibilities of components, right? So I have to sum up u1 squared plus u2 squared plus u3. And why did I call it turbulent kinetic energy? What is kinetic energy in physics, in dynamics? Do you remember this from dynamics? 1/2 mv squared. Have you seen this? Was the kinetic energy associated with movement of objects in the physical world? Newtonian mechanics is some object with mass m moving with some velocity. Its kinetic energy is 1/2 mv squared. Somewhat analogous to that, we define turbulent kinetic energy, which is 1/2. Of course, I removed m. I could normalize by mass. So it's sort of kinetic energy per unit mass of a moving turbulent flow. Then I have I'm adding the velocity fluctuations. This is some sort of a kinetic energy associated with fluctuations. It's not associated with mean flow motion. If flow is moving with no fluctuations, turbulent kinetic energy is 0. This energy is associated with fluctuations or eddies. Okay, so that's how I define it. Now, I want to do some work to determine the fate of the inconvenient term, the Reynolds stress term. What can we do to it? And the next part helps us discuss that. It's called anisotropy. So here you have to be careful with what I say. The difference between shear stresses and normal stresses is dependent on the choice of a coordinate system. It's a very delicate statement. Why? Okay, I tell you U1, U2, U3, or U1, U2, U1, U3, U2, U3. I can combine any of these two pairs. But what I calculate depends on the direction of my Cartesian coordinate system, the reference frame. If I rotate this, U1 is no longer U1, U2 is no longer U2, right? If I rotate the reference frame, these components change. The question is, do I calculate the same stress tensor components? See what's happening? It depends on the orientation of your coordinate system, whether or not your stress tensor would remain the same. And so an isotropy deals with that. The intrinsic distinction implies that the isotropic component of the stresses would never change. Okay? Regardless of the choice of a reference coordinate system. But the anisotropic part would change. Well, by definition, we said the flow is isotropic if rotation of the coordinate system doesn't matter. Remember that? That's from chapter 3. So some form of a Reynolds stress tensor, or somehow they're combining its terms in a specific way, will make this the combinations isotropic, in which the rotation doesn't matter. Some way of combining it would define it so it does matter, right? And you can do that. How? Remember, the Reynolds stress term is this. I and J could be anything. You could have 9 possibilities here. What I want to do here is add and subtract a term to this Reynolds stress. How? I subtract I subtract 2/3 of the kinetic energy and a delta function, and then I add again 2/3 of the kinetic energy and the delta function. Anybody remembers what delta function was? Delta function Ij is equal to 1 if what? I equal to j, and it is equal to 0 if I is not equal to j. So just using this delta function to put this formula together. And I claim that the first part of this to be an anisotropic part, which means that if I rotated my coordinate system, this term would change. Whereas the second term is the isotropic part. If I rotated the coordinate system, this would not change. Now, what is delta doing here? Well, remember, I could be talking about any component of the tensor. I could be talking about U1, U1, or U1, U2. I could talk about any 9 pairs of combinations. As a result, this delta may or may not be 1. I mean, if I'm looking at the same component, U1, U1, delta 1, 1 is 1, so this term remains. Okay? But if I'm talking about the shear component of the stress tensor, if I was looking at U1, U2, delta would have been 0. Make sense? But whatever happens, whichever choice of U1, UI, Uj, and whichever choice of the rotational position of the coordinate system, you will find that this first part is anisotropic. That means you calculate the same thing, regardless of the orientation of the coordinate system. Anisotropic, it would be different, but isotropic, this part would be the same. This is like a mathematical trick. It's just the way I want to develop the equations and use them further down. The anisotropic part is also known as anisotropy, and it's a physical quantity in turbulent flow. I mean, if you open a textbook in turbulent flow, there may be discussing this quantity. I mean, think about it as like density or velocity or Reynolds stress or temperature, a quantity. Anisotropy is a quantity in turbulent flow, and you can calculate it, you can formulate it, you can use it, you can simplify it, right? So this first part is called anisotropy. And we use the symbol A. So this we know as A, I, J. Can you tell me if anisotropy is a vector or is a tensor? How many say vector? How many say tensor? Tensor, because it has 2 components of direction required for its definition, A, I, J, right? Now, what I want to do, I want to rewrite my Navier-Stokes equation for momentum now using this anisotropy. The first thing I should do is to combine Reynolds stress and the pressure term in the momentum equation. This must be done for you to do anything useful to the momentum equation. So let me explain to you what I did. Remember, in the momentum equation, we had the sum of Reynolds stress term, spatial derivative of it, plus spatial derivative of pressure. This term was in the momentum equation. And if you're not convinced, I can show it to you again. Right? These 2 terms were there. I had the sum of Reynolds stress term and the pressure term. At that time, I called them Reynolds stress and the normal body forces, but this P was the pressure. Okay, so I have a sum of these. Here, I want to reformulate that sum using an isotropy. So the first thing I do, I replace the Reynolds stress by an isotropy plus 2/3 of K delta. Okay? I keep an isotropy separate. I have a spatial derivative. What happened was the isotropic part is now absorbed into pressure. I mean, in a way that I'm taking a spatial derivative xj of the sum of the two terms, the pressure and the isotropic part. I just regrouped some of these terms. You will see why this was required. But for now, just be satisfied that you can reformulate these two terms. So again, let me remind you, this is anisotropy. And now this new term, you can think of it as some sort of a modified pressure. And it does make sense because pressure is pressure in the flow. Pressure is always a normal force in any fluid system. Pressure is always a normal force to a surface or a body, control body. We also said something about the normal components of the Reynolds stress tensor, U2, V2, W2, or U1 to U2 to U3 to. They're also normal components of the Reynolds stress. So it makes sense to group them with pressure because they would both exert a force normal to the surfaces of the fluid control volume. It has the same effect. That's why it's grouped likewise with pressure. And we can call it modified pressure. So if you like, modified mean pressure is the effective pressure that comes from normal pressure as we know it, plus the Reynolds stress contribution to the pressure. So the Reynolds stress changes the pressure, the pressure that you feel or sense. And that's why you call it modified mean pressure. It's a new form of pressure. Okay. I'm not finished yet, right? I just grouped these terms. I haven't yet said what I should do with this anisotropic part. I will in the next few pages. Now I want to discuss the mean scalar equation. First I want to show you how I would deal with the transport equation for mean scalar equation. Then I will do it for momentum. Because for momentum is a little bit more delicate. It's easier to start with the passive scalar equation. So you see it being done once. So you would see the tricks and the approach. Then we'll do it. We'll apply to momentum. Like momentum, you can decompose passive scalar based on the Reynolds decomposition, which means that any instantaneous value of the passive scalar, this could be concentration of some gas in air or some contaminant in water, phi. Phi was a passive scalar field. The phi itself was not a vector, it was a scalar, but it still was a field because it depended on position vector x and time. So this was a field. I can still express it as a mean scalar plus a fluctuating scalar. And again, if you brought a sensor here and measured the concentration of CO2, let's say here, it would fluctuate. Right? Anytime you speak, there's a new burst of CO2. CO2 would fluctuate anywhere you measure. That's why you can express passive scalar as a sum of the mean and the fluctuating part. So, and here I used symbol phi prime to show the fluctuating part. So you can do the same Reynolds decomposition for any flow property if you want. But let's see what happens to the transport equation. before we deal with the turbulent part, well, we showed you this before. I mean, if you remember, I put this equation up in the previous chapters, where phi is the instantaneous passive scalar. These two are sort of material total derivative. Which now I have expressed as the sum of the two storage and advection parts. But really, this was the same thing I showed you before, and then we had a diffusion term, which was the diffusion coefficient Laplacian of the passive scalar. Now I should deal with this term up here. Now again, I have a product of velocity and the passive scalar. Again, these are instantaneous fields. I should deal with the means and the fluctuations. And I can expand each one as the sum of the mean plus fluctuation. I can carry the multiplication, and whatever that remains will be the product of the means of velocity field and passive scalar field plus the mean of the product of the fluctuations of the two. And again, some of these terms will end up being zero, right? So that term will be zero. Likewise, this term would eventually be zero. That's why the mean of the product greatly simplifies. This term, the second term, is known as a scalar flux. And it contributes to flux. I mean, what is flux in physics? What is flux? Flux is rate of transport per unit time per unit area. So flux of some quantity over a surface is how much is that quantity going through that surface area per unit time per unit surface area. This we know as flux. We define two types of flux here in this example. So we have a mean flux and we have a turbulent flux. Okay. So this we know as mean flux. This we know as the turbulent. And this is a big deal. I mean, anytime you do any transport analysis, I mean, air pollution dispersion. Okay, there's some pollution here, and that moves through a water treatment plant or an air domain. There is a flux of that pollutant in the domain. So this pollutant is going to go by the mean motion of the fluid. Okay, so that's called the mean flux. But there's also a turbulent flux, which is the type of transport associated with fluctuations of the fields. That's an extra mechanism that could enhance the total flux. And if you like, you can call this total flux for the sake of completeness. Okay? Now, subbing this back into the equation up here, I can rewrite now the transport equation for the mean passive scalar, which is that equation. So the product is now replaced by this term, and I can in fact regroup these in a special way. If I bring this term to the right hand side and I factor out a nabla, you can do it. You would get this. So you got the nabla of the diffusion coefficient with the gradient of divergence of a gradient of the field, you would get the Laplacian, you get the Laplace squared, assuming this diffusion coefficient was constant. But the divergence of the turbulent flux is what remains. So you see, you can group these two terms on the right-hand side. So this equation shows another instance of the turbulence closure problem. So again, now we have an equation, but we have a new variable which we don't know what it is. You see what happened? So I reformulated that equation. Still, I'm not done because I have a new term which I don't know what to do with. I need to come up with another equation to close this unknown term. So another instance of turbulence closure problem. And now I'm going to do that. Now I'm going to show you how I'm going to deal with this. So now I'm going to come up with a new equation to approximate that turbulent flux. And this part is called gradient diffusion and turbulent viscosity hypothesis. How do we determine the fate of the unknown term? One of the earliest people that tried something like this was Joseph Boussinesq. He was a French mathematician who came up with this approach and hypothesized that the mean scalar flux is in the direction and proportional to the negative mean scalar gradient. Okay? This was later known as gradient diffusion hypothesis or turbulent viscosity hypothesis. Any turbulence model you use nowadays in any commercial package like Fluent, CFX, or if you do OpenFOAM, if you run any open source fluid dynamics model, lots of these models such as gradient diffusion models in them. Okay? And the hypothesis can be shown as this equation. If the proportionality of the constant proportionality essentially took the diffusivity is constant, you can write it as this equation, and this constant as it would be would jump out of any possible derivatives or gradients or divergence terms. But if it's not constant, you have to deal with it further. But anyway, let's not be sidetracked too much with this what gamma is. But here the main idea is the turbulent passive scalar flux. This was the unknown term. Is now a function of some constant of proportionality times the gradient of the mean passive scalar. So why is it formulated this way? It says something like this. If there is variation, spatial variation of some quantity, like CO2 concentration, the turbulent flux will always be in the negative direction of that change, or a spatial distribution. Let's say if I have high amount of CO2 here, high concentration of CO2 here, and low concentration of CO2 here, what would happen? CO2 would flow from high concentration to low concentration. Same thing with heat. If I have a hot parcel of fluid here and a cold parcel of fluid here, which direction would the heat move? Always moves from hot body to cold body. See what I'm saying? That's why the direction of the flow of the turbulent flux is opposite to the spatial gradient of the mean quantity. This negative explains it goes from hot to cold. It never goes from cold to hot. Or it never goes from low concentration to high concentration. This is naturally how energy and mass move in according to the second law of thermodynamics. But it's not as easy as it appears. Why? This subscript T that appeared here is for turbulence, right? This subscript T which tells you that the concept of proportionality is not really a constant, and it could depend on a lot of things. First of all, this diffusion constant is not the molecular diffusivity. It's the turbulent diffusivity. It's a form of diffusion that appears because of fluctuations in the flow. Okay, it has nothing to do with molecular. And you should very carefully distinguish between the two. However, it's formulated in a way that you can combine it or absorb it into the molecular diffusivity. In other words, you can, if you want. Oh, by the way, let me just annotate. This negative means down gradient. So this negative is the down part of the gradient, right? Down. This nabla is the gradient. See what happened? When you say down gradient hypothesis, means that the turbulent flux is negatively correlated with the gradient, so it's down the gradient. It flows down the gradient. Now, I can absorb this turbulent diffusivity into the laminar diffusivity and molecular diffusivity or laminar diffusivity and come up with a total effective diffusivity. In any flow, both types of diffusion exist, even if the fluid did not move. If you had some CO2 concentration here, even if nothing moved, that concentration would diffuse out. Agree? Now that the fluid is moving, and it's moving in a turbulent fashion, there's an extra component of diffusivity, which is turbulent diffusivity. If you combine the two, you get the effective diffusivity. Now, be very careful. This turbulent diffusivity is also a field. Why is it a field? Because it depends on position vector and time. It varies in space. It's a field. It's not a constant. Its magnitude, it depends on the type of flow. But the molecular diffusivity is a constant, right? So it's a little bit simpler. The effect of combining this constant molecular diffusivity and the turbulent diffusivity gives you a new field. I mean, because one of those components was a field, right? So this is also a field. And finally, I can close my transport equation for passive scalar. Now, this is a closed formula. There's no surprises here. There's no unknowns. I know exactly how to deal with this. So if you like, this equation is now closed. Closed equation if the effective diffusivity is known. So that's what we mean by closed. So we now know how to solve this. I mean, if I gave you some boundary conditions, and if I gave you a computer, you could write a program to solve this. It's no longer open, it's closed. Now, so you saw one example of how you can close a turbulence equation and practically use it. But we haven't done it for momentum yet. Let me do it for momentum. For momentum, there's a little bit more delicate. For the mean momentum transport equation, the gradient diffusion hypothesis is more delicate to implement. In this case, we should relate the anisotropic part of the Reynolds stress to the mean rate of strain. Okay. Well, left-hand side is the anisotropy that I defined for you earlier, right? So this is A, I, J. I mean, no arguments. On the right-hand side, I have, if you remember from an earlier chapter, we knew this as Sij. Was Sij a vector or a tensor?
Tensor.
Tensor, because it has takes two directions, I and j. So I'm telling you that an isotropy and rate of strain are related, and there's only a constant of proportionality in between. Right? This is a very good approximation. It's a very practical approximation. And this symbol, what should I call it? If you want to come up with a name, if you want to have a guess. We knew for what viscosity. If I put a subscript T, it becomes 1. Turbulent. Turbulent, kinematic, viscosity. So I'm telling you that the constant of proportionality between the anisotropy and the rate of strain was only this turbulent kinematic viscosity. Note that I put an overbar on this rate of strain because I'm calculating for the mean velocity, not for the instantaneous. Right? So be careful here. Also, there's a factor of 2, right? Because, well, in fact, this was 2 times the rate of strain. Rate of strain had a factor of 1.5 in front of it, right? The factor of 1.5 is not here, so this must be equal to 2 times rate of strain. And the 2 jumps up here. So this is, again, another form of down gradient hypothesis, right? Because this negative is sort of a down, and the rate of strain itself is some sort of gradient. Rate of strain is a gradient. It is a bit of a more complicated gradient because it has a sum of a few gradients there, but if you agree with me that you're talking about velocity gradients here, right? Spatial gradients of velocity. So again, I have another form of a down gradient formulation. It's so so much so that this was a gradient, right? Spatial derivative of mean passive scalar was some sort of derivative. So is rate of strain. So again, I came up with another closure technique for the momentum equation now. And now I can put it all together. I can put it all together here, where this is the momentum equation. On the left-hand side, I have material derivative of mean. So that's the mean velocity. Here I have effective viscosity, kinematic viscosity, and then I have mean rate of strain, and then finally I have the modified pressure, which was pressure plus the normal contribution from the Reynolds stresses. Now, why did this effective viscosity come up? Of course, there's always molecular viscosity. So even in laminar flow, fluids move according to viscosity. There's sort of fluid friction. So this is a constant. But this new turbulent viscosity is now a field. This depends on space and time. If I add the two together, I get the total effective viscosity, which is also a field. And that enabled me to close this equation. So closed if effective viscosity is known. So that was another example of closure. You must be very careful. I mean, why did we have to separate this normal component contribution from the Reynolds stress test? Why did I have to separate that from Reynolds stress? Because the down gradient hypothesis is only valid for the anisotropy. You see the delicacy here. So it's only the anisotropy that's proportional to rate of strain. Reynolds stress itself is not proportional to the rate of strain. Okay? That was the very reason I had to define anisotropy in the first place, so that I could use the down gradient hypothesis. And that's why this other normal component had to be factored out and absorb the pressure into the modified pressure. So again, effective, nu F, effective is the effective viscosity, and mean pressure plus 2/3 density times kinetic energy is the modified pressure. Similar to the other chapter where we talked about Prandtl and Schmidt number, and we said these numbers come up if you have heat and mass transfer. In turbulent flow also, two new numbers pop out of the equations. These are the turbulent Prandtl number and the turbulent Schmidt number. The turbulent Prandtl number gives the ratio of turbulent momentum diffusivity to heat diffusivity. It's very analogous to what I told you before. But for the turbulence case, likewise, the turbulent Schmidt number gives you the ratio of momentum diffusivity to mass diffusivity. Which means that if you are solving flow problems involving heat and mass transfer, you need 4 of these numbers if the flow is turbulent, right? If the flow was laminar, you would only need the laminar Prandtl number and laminar Schmidt number, finished. But now, if the flow is turbulent, you need the laminar versions of these two, and then you need the turbulent versions of these two. That means the turbulent Prandtl number and the turbulent Schmidt number. So you need 4 properties to close and solve the equation. And that will be the end of the discussion for this chapter. And I have 2 minutes. Let me quickly solve a problem for you. Any questions about the material? I want to solve problem 3, but looking at the time, I don't want to rush it. So I'll solve that problem at the beginning of next lecture. Okay? But what did we do in this lecture? Let's just wrap up and put our heads around. We developed the transport equations for turbulent flow. Transport means Navier-Stokes equations. We came up with the differential equations that express motion of turbulent fluids. We did it for momentum, and we did it for a passive scalar. Okay? Now, on top, we showed you how a new term pops out of these equations because of Reynolds decomposition. A new term popped out. So this was the covariance of U1, U2, but the product of the fluctuations came up. Or phi prime, which was fluctuation of passive scalar or concentration and a component of velocity. And then we showed you a technique how to formulate this new unknown term, right? This is at the very essence of developing transport equations for turbulent flows. You have to write the equations out, see if you know a term or you don't know it. If you don't know it, you have to come up with some sort of a recipe, a solution, an approximation to formulate that unknown term, and finally solve all of your equations by hand or by a computer. Okay? And the technique we showed you for closing the equation was called gradient, down gradient, or turbulent diffusion hypothesis. It's a very important hypothesis. It's been used all over the literature and all over the sort of techniques makes use of this hypothesis and solve real flow problems. But it's not the only hypothesis. It's very limited, it has very limitations, only applies to certain types of flows, and there are many different ways to close turbulence, equations of turbulence. There's many different techniques, and we will discuss some other one of those in the future. Okay? Sounds good? Fantastic. Any questions? So we'll move on. Please continue your computer assignments, do programming and crunch numbers. The material will settle if you engage with the computer assignments. So see you next time.